So today we're going to talk about some chemistry that will come into play for next week's lab, where you'll get into cross-linking polymers. And to understand that, we need to understand molecular interactions and charges. In particular, we'll talk today about hydrogen bonding. And I want to make, before we get into that, I want to make one other announcement for people that, and I'm going to put this on BSpace as well, because I forgot to announce it on Wednesday. But I'm going to give everyone about 2 weeks to send me, if you have a conflict with the exam time, and you can't be there because of you're in a sport activity. It is on the Sabbath at after 7. I apologize for that, but that's what was given. That was a deck that was dealt to me, or hand was dealt to me. In those cases, religious conflict, a sporting event, an unforeseen anything that is a valid excuse, then you need to email me your name, obviously, and what time or date you could take the exam. And likely, I'll issue the exam to you beforehand. And there'll be a group of you, and I'll take care of it that way. But I'm going to give you 2 weeks. It can't be something that pops up later, in the semester. It really needs to be. You really need to be on top of your schedules now. Okay, I'll put that announcement on BSpace. So today we're going to talk about charge, and we're going to talk about how you compute a formal charge on a molecule. So formal charge, there's a very simple formula where we just need to know in this formula the number of, and I'll put this is the number of valence electrons in a particular atom in a molecular system. And from that value, we'll subtract the number of lone pair electrons. And we'll subtract exactly 1/2 times the number of bonded electrons. Another way of thinking about that is subtract the number of bonds, because as we all know, there are 2 electrons in a bond. So with this simple formula, you can compute the formal charge of any atom in a molecule. And as I'm making fun here, we'll look at formate. So we'll get formal with formate. That's supposed to be funny. Sorry. That sounds like forced laughter. Okay, that's real laughter. All right, so this is formate, and has hydrogen, carbon, and then these 2 oxygens, which I've drawn differently. Although if you know anything about organic chemistry, you know that those actually would be in a resonance with one another. However, what we'd like to do here is use our formula and figure out what the charge is on each of these electronic configurations around these atoms. So let's think about hydrogen first. That's easy. So how many valence electrons does hydrogen have? Yeah, that's good. 1 valence electron. And how many are lone pairs? 0. There's an I there. And then there's 1 bond, right? So there's 2 electrons in that bond. So 1/2 times 1 is 1/2 times 2 is 1. Okay, so in our formula for a formal charge, I'll just abbreviate FC. 1 minus 0 minus 1 is 0. So the formal charge on this hydrogen is 0, and I'll just put a 0 there. That should be pretty well understood. Now let's move over to carbon. Our carbon atom is here. Okay, how many valence electrons in carbon? 4, good. 6 total. The first 2 are in that inner orbital. We're not going to consider. They're not the valence on the outer shell. 4 in the outer valence shell. How many are lone pair? 0. And how many are in bonds? So times 1/2. There's 8 electrons in bonds around the carbon. It makes 4 bonds, 2 in each. It's 4. 1/2 times the bonded number of electrons. And so that again will be formal charge is equal to 4 minus 0 minus 4 is equal to 0. So again, we can put a little 0 there to denote that carbon has no formal charge. So now it's going to get more exciting here. We'll do oxygen. We'll do this. I'll just designate this oxygen this way, so you know which oxygen we're talking about. This particular oxygen in the carbonyl. Okay. And so how many valence electrons are in oxygen? 6 valence. I'm just going to put a V. How many are in the lone pairs? This looks like 4 lone pair LP electrons. And how many bonds is it making? 1/2 times the bonded electrons. So there's 2, right? So there's 1/2 the bonded electrons. So that means for this oxygen, the formal charge is equal to 6 minus 4 minus 2, which is 0. No charge on that particular oxygen, and we'll put a 0 up there. Okay, I saved the best for last, and that is this particular oxygen. And again, 6 valence. How many are lone pairs? There's 6, right? Lone pair electrons. And 1/2 times the bonded is 1, correct? So the formal charge on this guy is going to be a negative number. 6 minus 1 is equal to minus 1. That is its formal charge. And typically what you would do is you designate that. Some people put like a minus sign with a circle on it like this to designate, of course, that particular atom in the molecule would have a negative 1 formal charge. If you wanted to, you could put a minus 1 there. That would be fine too. So overall, for this particular molecule, the total charge of formate is equal to 0 plus 0 plus 0 plus minus 1, which is minus 1. That's quite obvious. And if you took this equation that we've shown here for formal charge, and you consider that all these atoms are together, and of course they share bonds with one another, then I'll show you in a bit that with a slightly different equation, you can calculate the charge of the whole molecule in a little more simplified manner. And we'll do that as a clicker question together. And we'll do that in a minute. But we'll do one more example before we get to the clicker question. So we're going to do borate, because borate is going to be the molecule they're going to be using as a cross-linker in your experiments. So borate looks like this. As you can see, it has 4 OH groups around it. And the question is, well, what is the formal charge of this thing, the various positions? Unfortunately, because of its symmetry, we only have to consider oxygen, hydrogen, and boron. And we'll do the boron first, since we haven't run into that guy yet. That has 3 valence electrons, 0 non-bonded or lone pair electrons, and 4 in its 1/2. 4 in its 1/2 times the number of bonded electrons, making 4 bonds. As 8 electrons times 1/2 is 4. So then our formal charge for boron is 3 minus 0 minus 4 is equal to minus 1. So again, we would, if you were to designate this on a structure, you do it like this. Typically, and we'll get to it's a little more nuanced than that, but in this particular formula here, we could then put a minus 1 there instead of the question mark. And that would designate that this ion has negative 1 charge, because as we've already sort of examined, the hydrogen, of course, is going to have no formal charge, because hydrogen is going to essentially be 1 valence, 0 non-bonded or lone pair. and 1 in its 1/2 bonded. So that's again going to have an FC of equal to 1 minus 0 minus 1 is 0. And the oxygen in these alcohol groups is going to have, again, 6 valence electrons. It's going to have 4 lone pair electrons, and then it's making 2 bonds, so 2 for 1/2 bonded. And so that's 6 minus 4 minus 2 is 0. So as you can see, we're not going to do every single oxygen. They're all the same. The only charged moiety in this atom, in this molecule, is a boron by this formal charge calculation. So, those are 2 examples, and you should be able to now, hopefully, if you see one of these on the exam, compute formal charge on any atomic position. Is there a question? Anywhere? Question? Is that pretty straightforward? Okay. We can either do a little bit more, or while this is fresh in our heads, we can do a clicker question. You guys want to go for the clicker question? You ready? Okay. So get your clickers out. Make sure they're set to AA frequency. Yeah. You shouldn't unless you played with it. Yeah, don't change your frequency. Okay. So this clicker question is set up now so that, okay, so before you start clicking away, don't click yet. Okay, read the instructions. So one of these molecules I've designated with the incorrect charge, okay? And it's your job to figure it out. But instead of making you compute every single atom, that's kind of laborious, right? I'm going to give you a shortcut formula for computing the entire constellation of atoms in that molecule at once. And to do that, the hint tells you the formal charge is the number of valence electrons of all the atoms, you add them up, and then minus the number of electrons in the molecule, okay? And from that, you should be able to determine which of these is incorrectly labeled as the incorrect charge associated with it. And so that's the shortcut formula that I was alluding to earlier. So I'll give you a good juicy 4 minutes or so here to cogitate on this. You can even consult with your neighbors, okay? This can be group work, because I know this is a little bit harder. So feel free to talk it up. Yes?
Oh wait,
that's good.
Just kidding.
Yeah.
Okay, sorry, never mind.
Okay.
I'm kidding.
Oh, I haven't turned it on yet. Sorry. Okay, I need to turn on the program to record your answers. I was giving you some time to think about it first. So pardon me while I turn it on. Sorry. Okay, this question is now live, okay? You can change your answer, But we're just doing this for participation purposes. Okay, I'll give everyone 1 more minute, but it sounds like people have reached an answer. You can't hear me? I don't know how to turn it up. Oh, got it. Better? Okay. All right, so that is our exciting clicker question. There's still answers coming in, so I'll let them trickle in. And we'll see our exciting graph to see how whether I taught this concept or not effectively. Okay, I'm going to stop now. Looks like they settled in. Oh, still a few more. Click, click, click. 421. Is that somebody still clicking? I did say I'd give you 4 minutes, but I gave you a couple minutes and I gave you a couple minutes to click in. I'll give you till 2 minutes here. All right. Last straggler. Sorry. Okay, so many of you picked the right answer. You picked C. Okay. And 7% picked acetate. Somebody picked E. See me after class. We still do paddles, All right. I'm just kidding. All right. So where's the? Okay. So all right. So if you're doing it by the formula, there are your answers. You basically, you count up your atoms. So you have 3 hydrogens. That's 3 plus 2 carbons. Carbons are how many for the valence? 8, right? That's 11. So 11 plus the 2 oxygens is 12. 11 plus 12 is 23. 23, and then you count all those bonds and lone pairs, and you're going to get 24. They're in even numbers, remember. You should always know, because there's no radicals, okay, on the board, all right? No radicals up there. All right, so oxygen, two oxygens and a carbon, that's 16. That's 12 plus 4. And if you count those bonds up, you have 16 total. And then it gets interesting here with this azide on the end. That's carbon dioxide in the middle. The one on the choice A is acetate ion. And then we have an azide ion here. And you can see the nitrogens are worth 15 valence. So I got 15. Then you count those bonds and those lone pairs. 2, 4, 6, 8, 10, 12, 14, 16. 15 minus 16 is negative 1. But it says it's a positive 1 charge, so that is the answer. All right, for those of you that missed it. Now, if you want to compute the charges on all the atoms, this is what you would get. Okay, if you follow the original formula I gave you, which would take you a long time to do, then you get this. And you can see the azide kind of cute. It goes -1 plus 1 minus 1. So it's kind of an interesting example, which I'm showing you that just so it's kind of fun. Okay. All right, so that was good. That was exciting. Hopefully, you will now remember formal charge. I want to get rid of this little. Okay, so the thing about formal charge in this Bohr example is it's grossly, it's correct in a formal sense, but it's not correct in a real-world electronic structure sense. And the electronic features around this borate ion are going to be much different than just simply a strong negative charge over the boron. And so this is where we need to think about what the actual charges are, or the partial charges are, in this molecular system. And partial charge determination requires an understanding of your electronegativity scale. And remember that this was established by Linus Pauling, a great scientist with several Nobel Prizes, one a Peace Prize and a Chemistry Prize. And this scale, if you recall, if you go to your periodic table and you look at fluorine, that is the king of the hill. That's the most electronegative atom on the periodic table. So you'd say it's very or strongly electronegative. Ugh, not writing well. Strongly electronegative. And next to fluorine, you might say oxygen. And I'm doing this by their actual electronegativities values. I'm not going to draw every atom in the periodic table, but I'm just going to show you the ones that would make sense in considering borate and those in between. I'll put sodium on the end, and you can see sodium is very weakly electronegative. And so, if sodium and fluoride were around one another, the sodium would be very happy to give up its electron so that it wouldn't have this just one electron in its outer valence and a shell. And fluorine would be more than happy to take it because it would go from 7 in its valence shell to 8, and it would satisfy octet rule. And you get a strong ionic interaction between that fluoride and that sodium. So that's one aspect of this that you can consider in ionic interactions. But the other thing to think about are what we call dipoles. Okay, and a dipole is an arrangement between two atoms. For example, if we think about an alcohol group, hydroxyl group, whether it be in, say, an alcohol or in water, you have the situation where we know that the oxygen is more electronegative than the hydrogen. And so what we would tend to imagine is that we would have this situation where, on average, some of those electrons that are shared in this bond between oxygen and hydrogen sort of maybe drawn a little more, drawn in toward the oxygen more often, okay? So that means that on the hydrogen end, you'll have a partial positive charge, and on the oxygen end, you'll have a partial negative charge. And then so what I've drawn here, and I'll do it in blue, is I have drawn a dipole where the arrow shows the positive end is the more positive end of this dipole, and the negative end is the tip of the arrow. And so what you can think of these dipoles are like little bar magnets, okay? If you ever put bar magnets near each other, and they're sort of allowed to freely rotate on a desktop, you notice that when you bring one near the other one will orient relative to the magnet you're bringing in. And essentially, you have to think of these in the same way. These are electrostatics and not magnetic interactions, but you see with simple bar magnets, but the same idea applies. That you have these two poles, one has slightly more negative charge and one has slightly more positive charge. And if you bring two dipoles near one another, the negative end of one is going to want to orient towards the positive end of the other. And so that, if you have lots of molecules in solution or in a molecular configuration, lots of functional groups that have these dipoles, strong dipoles in them, then they will tend to make these interactions. You can get networks of interactions that way. And this explains like the interesting properties of water, like its boiling point, surface tension, and the hydrophobic effect, which hopefully we'll talk about later. So that's the basic idea. And I'll just make sure that since oxygen is more electronegative, then it acts as the negative pole of the dipole. And on the other hand, we have the hydrogen. Hydrogen is less electronegative. And it acts as the positive dipole. Positive end of the dipole. Okay. So back to borate, which yes. Question? We're just going to do it this way. It's fine. Yeah, designate which end by putting the charge there, and then you can assume the other charges. But on the exam, it would say, it's multiple choice anyway. So, but in your notebook, be sure to be clear on that if you're filling out these answers. So let's think about borate. There's basically two different types of dipoles in borate to consider. So we have the hydroxyl, which we've just drawn here. That's one dipole, and then we have the oxygen boron. And again, boron being much less electronegative than oxygen. So we have these two dipoles. So that means that boron is not going to be a big, center of negative charge in this molecular system, which is what you would have thought from the formal charge calculation, correct? So it turns out it's a lot more complicated than that. And you have this dipole. I'm not going to draw it for every case, okay, because it's obviously got this fourfold symmetry. But if you can imagine the oxygens, the more electronegative oxygens are going to want to take on a little more of this negative charge. They're more than happy to accept it because they're greedy toward these electrons. And so the negative charge actually would be more distributed around the oxygens and not around the boron. And so if you were to draw the partial charges, you'd use this lowercase delta symbol, and you'd say, well, these hydrogens are all partially positive, and these oxygens are partially negative. And the boron here is partially positive. So it turns out that in this case, it's kind of interesting that the boron is actually charge in reality, as it doesn't reflect its formal charge at all. So hopefully that's clear, and I'll give you a second to catch up, and then we'll get into hydrogen bonding. Okay. So now the idea is, of course, when you think about water, you realize, of course, these molecules are all freely rotating around and they're making molecular interactions with one another. One of the major molecular interactions they're making in solution are these dipole-dipole interactions, and we call these particular dipole-dipole interactions that water makes hydrogen bonds. And so here's a water. So here's a water here, and we know that it's partially positive on this end, and then here's its two lone pairs. Obviously, it's